So thanks for inviting me. I'm here to talk about a project that I've been working on with Guy in Amsterdam, as well as a little bit with Enrico, on trying to understand what instantons do when you start to look at them in real time. And as we'll see, this kind of torus thing will be a recurrent theme in this talk. So really, I'm primarily motivated by understanding axions. Axions, we know that they're these very nice inflationary candidates. And really, when I say axion, I mean a field that has a compact field space. And so it has, as I go around the circumference of the field, the theory comes back to itself because that's an exact redundancy of the theory. And at least in string theory, we know that the potential is only generated by non-perturbative effects. So,
we know that generically it's not, but you can restrict to this case if you wish.
yeah, okay.
Keep going.
Yeah, okay.
It's a choice, but go ahead.
Yes, yeah, it is a choice. What I'm going to be thinking about for this talk is taking this axion and coupling it to a gauge field through some Chern-Simons-like interaction. And we expect that the instantons of this gauge field are going to, classically this action, f wedge f, is a total derivative term. And so classically, the axion should have a continuous shift symmetry. But when I start integrating out the gauge field, there will be instantons, due to the fact that it has a compact field space as well, a topologically non-trivial field space as well, that will induce a effective potential. And generically, we compute this using some Euclidean vacuum-to-vacuum computation. And we know that this gauge symmetry, this redundancy, restricts the effective potential to be some periodic function on the field space. So the story of natural inflation is I have this cosine-like potential, and I put my axion, vacuum expectation value, up on the hill, and I watch it roll down. Now, we know that there should be some speed limit to how quickly the axion can move before this description breaks down. Surely, if I move quickly enough to start exciting particles, have particle production, the description of the axion as rolling down this effective potential without any friction-type terms will not be valid anymore. And so really the main question that I want to get at, and this talk is about as a first step to answering this question, is how large can the field's velocity be before the effective potential stops becoming a good way of inferring the semi-classical dynamics. And we know from the way we compute this effective potential that if I very, very slowly drag the axion up its potential, this should tell me about the vacuum energy of the theory. And so there should be some notion of adiabaticity. But the speed of phi is determined by this effective potential. So is it consistent to say that it rolls down the potential? Or can I take the axion and fling it over all the barriers so it goes up and down like that? So we can start to think about when this would not be a good approximation. And I emphasize that this effective potential is coming from a Euclidean computation, and we want to ask Lorentzian questions. But we can get a little intuition for why the answer might be dramatically off from our expectations by just looking at the dilute instanton gas picture. The dilute instanton gas approximation, you think about having a bunch of relatively localized instantons and anti-instantons that I sprinkle over space, and they all contribute to give me my effective potential. But if I restrict myself to very small times, I'm only going to pick up a few of them. So it might be that as I look at very short times, I only see the effect of a few instantons. And that might dramatically change the effective potential I see. So this is all really motivation for this work. And what I want to do in this talk is start looking at simple toy models to be able to and study this. So the simplest gauge theory is a particle in a circle. If I put a magnetic field going through that circle with some flux through that circle, then this induces a theta angle for that field. So its energies are, it's a trivial theory. The eigenfunctions are Fourier modes. The energies are just quadratic. And the theta angle gives me a shift. And so the effective potential, which should measure the energy of the vacuum state, is going to be just a bunch of quadratics that are pasted every 2 pi. But we can also do this computation in the same way we would do a quantum field theory computation. We have a bunch of saddles, which consist of paths that run around the circle n times. And if we do that, we get this funny infinite sum of cosines. And if you ask Mathematica what this is, it will give you some polylogs. And then if you wait for a week or two, you'll realize that it's just a bunch of quadratics. And so what this does, what this model does is it captures at least some features of just the gauge theory coupled to a theta angle. Yeah.
So we are doing 1 plus 1 d
0 plus 1.
0 plus 1, and now theta is not the position x.
Theta in this case is just the flux, the magnetic flux going through the circle.
Okay, so I have two fields, theta and x, and you integrated out x.
So this is just, here theta is a parameter, just the theta parameter. And I'm just studying how the vacuum energy changes as a function of theta.
Yeah.
Much in the same way, before I think of the axion as a dynamical field, I think about how the gauge field responds to changing the theta f wedge f term in the action. This is analogous. So from the point of view of the full theory, this is the particle in the circle.
So theta is the analog of
phi, yeah. And here it's not dynamical.
x is the analog of f.
Yes, yeah. So this captures a lot of the features that we would expect that we see in this quantum field theory model. And so we can ask a similar question: which instantons contribute at short times? So the propagator is very simple to write down. The most important thing is that at very long times, there's a preferred form of the propagator in terms of the vacuum energy, arranged in terms of the energies of the system. So very long times, the only energy level that contributes is the vacuum energy. And that's, well, it's not exactly this wave function, but it's something that has no nodes. At short times, there's a better description in terms of instantons, in terms of windings around this path. And at very short times, the only instanton that really dominates is the one with 0 winding. Now, importantly, in order to go from this picture to this picture, I need to know about everything. These two things are related by a Poisson summation, and that Poisson summation, if I'm going to express the vacuum energy, has to know about all of the instantons. At very short times, this guy knows about all of the energy levels. It has to know about the full structure of the theory, which is kind of what makes sense. At very short times, I should not just see the vacuum state. So again, the main question is, when does the effective potential fail to capture the dynamics, capture the actual dynamics? And there's been some work done on tunneling in real time, but what we really want is a simple toy model that captures all of the relevant features and essentially the analog of the double well that we can use to really study and answer every question that we might have in that simple toy model.
Was there an analog of particle production in this toy
Not yet. No. Yeah.
But what do you mean by effective potential here? Is it that solid line, or is it like solid line going up to that line?
That's a good question. Yeah.
Rotation is monotony, right? You don't expect your photon go like over this solid line. You expect if you go through the maximum, you expect it to go in the stable branch as well, right?
So yeah, yes. So the effective potential typically is written as like some cosine, right? And that when I go from one minimum to another, you know, there should be a way of going up the branch, but the effective potential, as it has been derived, only sees that single.
Effective potential, you really call this solid line.
Yeah, exactly. You know, the effective potential people write down is this. That was computed using a Euclidean path integral, and so that corresponds to this solid line. So you look at this particle in the circle. It's the simplest gauge theory. You see that there's a theta angle. You say, okay, well, how can I make this into an axion? I just promote the theta angle to a dynamical field or dynamical particle. And so you write down this model, and then you wait for a while, and you realize that it's a particle on a torus in a magnetic field. And again, this has the same effective potential as before. So you can interpret this model in two ways. You can interpret it as some sort of mini superspace model for the original quantum field theory that we're interested in, or it's actually the Schwinger model in disguise. So the Schwinger model is fermions plus a U1 gauge field. And if I put it on a cylinder, the only relevant degree of freedom for the gauge field is a Wilson line that wraps that spatial direction. And if you look at the low energy excitations of this theory, it's exactly the theory that it's exactly the particle on a torus in a magnetic field. So by studying the particle on a torus in a magnetic field, we can really understand the dynamics of this two-dimensional quantum field theory. So one aspect, one question that we really have to answer is, which state should we be evolving forward? Writing down the propagator in the particle on the torus and the magnetic field is very simple. This model has been studied in connection to the fractional Chern-Simons effect, turns out. Sorry, fractional quantum Hall effect. So the state space is known, the energy eigenvalues are known, and you can just write down the propagator. But it's very hard to take that object and extract any information about the actual dynamics, because the actual information about the dynamics is going to depend on which initial state I put in. So you need to choose the right initial states. And we're interested in semi-classical states. So we're interested in coherent states. It turns out that there's a class of coherent states that essentially look like this. I'm mainly going to be showing formulas for the particle in the circle, where you can write them on a slide. Particle on the torus is a bit more complicated, and I'll just replace everything with bold symbols when I go to that to denote matrices. But all of these coherent states have, they look essentially the same. You have a few functions, f, g, Langle-Rangle x, Langle-Rangle p, and the classical action, which depend on time. And these all solve, simple time ODEs. It's essentially a Gaussian that is set up to satisfy the Schrodinger equation. And so in the particle on the circle, if I don't put it on the compact space, it's just the free particle on a line. And it looks like a Gaussian that moves with expectation value this, and then it has a variance that spreads out in time. Okay. So in order to put this on the circle, we then image it around the space to form a well-defined coherent state on the circle. And we can then start asking questions about, you know, what does the theta angle do to the semi-classical dynamics of this system? It doesn't really do much, but unless we start waiting for very long times. Because if we wait for very long times, we should start to see differences in the vacuum energies and differences in the vacuum energies, which is really the only thing that distinguishes these two models. So it turns out that if you wait a very long time, if I have a particle with no theta angle moving at a velocity to the right, and I compare it to a particle with a theta angle with the same velocity moving to the right, then after a time t revival, they'll get displaced by amount given by the difference in their theta angles. So, you know, these states are very natural things to study from the point of view of, from the semi-classical point of view. They behave like nice, well-defined particles until a time where they've spread out quite a bit, and I can't really think of them as particles anymore. In order to ask questions about these things, we need to ask gauge invariant questions. Gauge invariant questions are those which respect the periodicity. For the particle in the circle, you have these vertex operators which give you sensible answers. And these are the things that we're mainly going to be interested in. You can think of them as this answer as having two pieces: an argument, which tells you where the particle is on the circle, and a length, the absolute value, which tells you how localized it is. If it's very well localized, then this absolute value is very close to 1. And it's a special fact about these coherent states that these expectation values split up into two different pieces. A piece that only comes from the non-compact answer. You know, if I take the coherent state and I don't image it around the circle, then I get this answer. But then once I put it on the compact space, I get instantonic effects. And that's in this blue space. It appears as a ratio of theta functions. Whenever you have periodicity, you expect theta functions to appear. And by understanding how this, you know, the argument of this, what phase this has, we can understand how these instantonic effects affect the semi-classical trajectory. It will also turn out to affect how localized it is. And it's typically the case that these things become very delocalized very quickly. Something that I don't think we still understand. So that was for the particle in the circle. We found a set of coherent states in the non-compact geometry, you know, and just on the real line. And then we image it around the circle to create a well-defined state for the particle in the circle. We can do the same thing in the toy model, and it's much more involved. So I've hidden everything away in symbols. But the main features that I pointed out on the previous slide still remain. I have a splitting between the non-compact space and the compact thing, which features this higher dimensional realizations of the theta function, the Siegel theta function, which encode the fact that I'm on the compact space. And then, so as I said, any phase in this compact term represents a deviation from the effective potential. And so if you're curious, the classical expectation of these states is just, you know, they execute sinusoidal motion at a frequency omega, which is set by whatever appears in the Chern-Simons terms, as well as the radius, the two radii of the torus and their masses. And there's, you know, it depends, each trajectory depends on the other particle. So what x1, which I think of as the axion, what trajectory that executes depends on the initial momenta of the second particle. And likewise for the gauge field, the second particle, they're interconnected. That's where a lot of the complication comes from. And so we can start asking questions about how do these states move? And exactly as you suggested, I can take this particle and then throw it and try and see if it sees the effective potential. But no, it just sees one branch. It doesn't see the fact that there's a hump there. It just continues to rise up. And so if I'm looking at plots of this particle as a function of time, mapping it onto the circle, then if it doesn't have enough energy to go over the barrier, it just sees a quadratic well. It sees the effective potential. But if it has more energy than that, then it will spin around the circle a couple times and then slow down and then sling back to its original position. So you can start to ask questions about this expectation value to get a sense for what's going on. It's highly state dependent. It's highly dependent on the parameters of the torus and the parameters of the model. I don't fully understand what are the relevant things in this model that lead to deviations in the effective potential. But for the classical piece, typically what happens is that the two particles, the axion and the gauge field, they execute the classical motion, but then they quickly become spread out on a time scale that's relatively short compared to the entire period. For the compact piece, however, this is a lot more dependent on the different parameters, but you do get deviations from the effective potential. Those deviations from the effective potential are seen by the fact that this line is not straight at zero. I don't understand what is the correlation between what the classical particle is doing and the what's happening here. But as I said, this is work in progress, and just wanted to show you guys and get your input on it. The instantons also have the effect of further delocalizing the particle, which is kind of to be expected. If the particle is spreading out and it can start to come back around to see itself, it's just kind of going to equilibrate until it reaches a period where it reforms into a nice shape. So to conclude, the main question that we want to answer is, when does the effective potential fail to capture the actual dynamics of the system? And we were really after finding a simple toy model where we can study every aspect of this and solve it exactly. And that ended up being the particle on a torus and a magnetic field. We constructed these coherent states, which should represent nice semi-classical states that one would use to do axion inflation with. And what we see is that there are deviations from the effective potential, and that the state doesn't like to be too well localized in its field space. So there are a lot of questions. What does this imply about axion inflation? The fact that it likes to be spread out, I kind of expect to be cured by inflation, because inflation tends to squeeze the state in its field space. How does this story change in 4 dimensions, or when I start having more complicated instantons? I don't know. I'd like to find out. And is there a helpful path integral formulation? Path integral is very helpful for if you know where the initial state is and where the final state is. I mean, you can do a Schwinger-Keldysh thing, but it's not entirely obvious that that's the right way of thinking about this. But yeah, so thanks for your attention.